Okay, last question for the Chapter 1 problem set. Problem number 25. Let's see. We got Part A. In summer of 1970, the pump price of gasoline was about 35 cents per gallon. Between 1970 and 2000, the average rate of inflation was about 5% per year. What might be the expected pump price in summer of 2000? What conclusion might one reach from this calculation? Part B. A PhD engineer starting his career in 1970 at a salary of $16,000 per year retired in 2000 at a salary of $80,000 per year. How well did his salary keep up with an inflation rate of 5% per year? Part C. Tuition increases at major private universities in the United States have led inflation rates by about 3% per year. Use this observation to suggest strategies for paying the future tuition of a child at a private university. Assume no financial aid, an annual inflation rate of 5% per year, and a tuition of $25,000 per year. Recall the compound interest formula. C of T2 divided by C of T1 is equal to the quantity 1 plus I raised to the power of a subquantity T2 minus T1, where C can be cost, salary, etc. T1 and T2 indicate times, and I is a rate, inflation, interest, etc., expressed as a decimal. Okay, this one seems fairly straightforward. No regression this time. I think it just seems like middle school algebra, to be honest. Now let's go. So part A. We're given a initial pump price and an inflation rate of 5% per year. Okay. So inflation rate, I guess, is the increase in cost of consumer goods, averaged across some basket of goods. So one big assumption we'll make is that this inflation rate will apply to gasoline. Big if, but I mean, what else can we do with this question? So, let's say as much for part A. It should be assumed that the rate of inflation is the increase in cost of a basket of consumer goods over time per year. The percentage increase, and that gasoline is and that the increase in price, the yearly increase in price of gasoline rises at the same rate as inflation. Okay. So 1970 to the year 2000, that's 30 years. So we could apply 5% per year. So let's see. 5% per year. So I'm going to do this. I mean, I guess we could just use that compound interest formula as is. So let's go with that then. We can reorient it so that we get a, there we go, a little bigger. Solve for C2. Let's go with this. Okay, let's solve for C2, so that will be C of T sub 1 times this stuff equals C of T sub 2. So let's see. Let's list some givens. What if we can do a sub part for this one? Subsection section. Oh, there we go. Part A. Givens are an initial cost. Let's list them. So cost of gasoline and the rate. So C of Ti or T1 equals, what was, how many cents? 35 cents per gallon. So 0.35 USD per gallon. And the rate is equal to 5% per year, so 0.05, I think. And T2 minus, let's see, let's just go with T1 equals 0 years. And T2 equals 2000 minus 1970 equals 30 years. Do we have everything we need? Yeah, I think we do. All right, so let's go ahead and add some numbers to these. Apply equation, and we'll give a label to that. Meta shift exclamation mark, problem 25, C T2 T C T2 C T1. All right, let's see if that works. Apply equation, meta shift question mark, problem 25, C T2 T C T1. Okay. Plug givens into equation, blah, blah, blah. All right. Let's see. Let's first solve equation for CT2. The cost of gasoline in the year 2000. Then plug in givens in. All right. All right, CT1 equals 0.35 USD per gallon times 1 plus 0.05 raised to 30 minus 0, and I guess there should be some kind of a ratio in there, but I'm just going to ignore it because I don't want to get into that. This seems such a simple formula here. Yeah, to be dimensionally consistent, I have to do something like divide by some t reference, which make a cost equation. Yeah, I'd have to do something like that, divide by some t reference, which equals 1 year, just to make things work, but I am not going to do that. I am just going to keep it simple. Yeah. what have we got? I think, yeah, the units should just pop out. 0.35 times 1.05 raised to the 30 times, yeah, USD per gallon. And that will yield, just plug that into the calculator, 0.35 times 1.05 raised to the 30th power equals 1.513 USD per gallon. Okay, then what else we got? So that's the pump price you might expect in that year 2000. What conclusion might one reach from this calculation? I mean, besides the price? I'm having trouble reading between the lines. Are we supposed to read between the lines? Every 30 years, the price goes up by a factor of 1.513 divided by 0.35, a factor of 4-ish? I'll just say that. Okay, so in a period of 30 years, the price of gasoline, according to the model, to a 5% inflation model, after a period of 30 years, the price of gasoline increases from 0.35 USD per gallon to 1.513 USD per gallon. In other words, every 30 year. In other words, at 5% inflation, 5% annual inflation, every 30 year, the gasoline price roughly quadruples every 30 years. Yeah, let's call it good. Alt 3. Part B. Part B is, it gives us in 1970, a starting cost of $16,000 per year and ending cost $80,000 per year. And it's asking us to kind of do the reverse, which is to calculate I. All right, so let's do some givens. And down here, let's just plop this equation for now. Givens, we can just copy these, I think. And there you are. Modify them. So instead, the initial cost is actually, it's USD per something, but it's a year now. And what was that rate? 16,000 to 80,000. So 16,000 is that. CT2 equals 80,000. And I, we don't know, so that's what we're trying to find out. T2 equals 0, 2000, we got... Nope, that doesn't make sense. T2, I guess 1970. No, we're good. We're just doing something more explicit. All right, so we're given that. Solve the cost increase equation for I. So let's do that. Insert several equations. And let's solve for I. So we need to let's put in that thing in the equation. First, let's modify equation so that it is dimensionally consistent. This includes dividing the quantity T2 minus T1 by a reference time span of in the context of this part of the problem. In the context of this part of the problem, the reference time will be 1 year. So let's go ahead and copy this equation. Go ahead and divide, make this T ref. Let's go ahead and add this here, the reference time, and we'll explicitly state the variable that we're making. Let's go ahead and move the givens. Let's put it here. T underscore ref, we'll call it 1 year. Solve equation, and we'll do this one instead. Let's give it a label, problem 25. Problem 25, CT2, CT1, Tref. Meta shift X question mark. P25, CT2, CT1, Tref. So let's go ahead and copy that. Into here. And add in, make this substitution. Copy this, replace this here. And that just means that divided by 1 year Great. So now we can copy this and use that in part B right away. Let's solve the cost equation. Meta shift question mark CT2 CT1 Tref. Oh, that's right. I need to put the problem in there. Problem 25. There we go. For I. Let's go ahead and solve this for I. So first we need to take, let's see, take the natural log to get that out. So natural log of that. Actually, let's use brackets instead. Natural log of a bracket of this. And the main thing we're trying to get is this quantity in the exponent down times natural log of this guy. You can erase this. Great. And then we can divide this side by this. Yeah, divide that by that. I could do the reciprocal and do some weird thing. Oh, I gotta put time ref in here, don't I? Yeah, time underscore ref equals 1 year. 1 year equals, all right, natural log of, so we got I guess we need to exponentiate to get rid of the natural log again. So if we're going to do that, let's put, yeah, let's do what we were thinking of. Let's go ahead and, instead of dividing by this, that's the same thing as multiplying by the reciprocal. Okay. And let's get rid of the fraction. Okay, and then we're not changing this, so let's just omit this. Then we can insert the time thing into the cost. All right, so we can put this into a quantity and then raise that to a power itself. There. That then equals our thing, which we haven't changed. Oops. Which now we can remove, exponentiate everything and remove, yeah, so 1 plus I. And then let's go ahead and flip everything over. Oops. 1 plus I. I equals this thing minus 1. Subtracting 1 from both sides. Okay. That should do it. Does every step make sense? I start off with original equation, take natural log. That allows me to pull the, oh wait, where'd this go? I Must have cut it. Yeah. There we go. Equals that, and then that's when I... Oh, that's what I did. That's better. So taking the natural log of something that's raised to an exponent, that exponent becomes a product outside the logarithm, and then we divide by that product. So we get that on the other side, leaving this behind. And then since this itself is a fraction, we flip that over so that we can get it like this, and then we can use that as an exponent here of this quantity. We have a logarithm of big stuff inside, and logarithm of the big stuff inside, we simply remove the logarithm by exponentiating everything, or in other words, raising everything by, like, taking everything on both sides and having e raised to that power. We're left with this. Then we just solve for I. We get I. Great. And did we say anything? Yep. Solve equation 445 for I. We've done that. Now plug in given values in order to calculate I. And did we list the givens? Yes, we did. 16,000, 18,000, 30, 1 year. Okay. Let's do that. Copy that. Insert multiple equations. Okay. Remove that number because we're not actually doing anything yet. All right. So first quantity, 80,000, I think. 80,000 USD. 16 comma tab 00 USD. Gotta put that tab in there so that the commas work correctly. Another fraction, 1 year divided by 30. No, not yet. 30 year. Take that whole thing, minus 1. So everything's dimensionless. Great. Let's go ahead and put that into our calculator. See what happens. So quantity 80,000, 80 divided by 16 raised to the quantity 1 divided by 30. Subtract 1. Okay, so that is equal to 0.05511, which is equal to about 5.5. I is equal to approximately 5.51%. Any sig fig issues here? 2 sig figs, I guess. Let's do 5.5%. Great. So his salary, the engineer's salary increased at a rate. Salary increased, had an average annual. The rate of increase of the engineer's salary from between the years 2000 and 1970 was, let's do the average rate, 5.5%. This is 0.5% higher than the average rate of inflation for that same time period, The engineer's salary was slightly outpacing inflation. Okay. Part C. Tuition increases at major private universities in the United States have led inflation rates by about 3% per year. Use this observation to suggest strategies for paying the future tuition of a child at a private university. Assume no financial aid, an annual inflation rate of 5% per year, and a current tuition of $25,000 per year. Tuition has led inflation rates by about 3%. So tuition rates are 8%? I'm pretty sure it's a lot higher, but all right. Part C. Givens. We are given. Well, let's see. What is it? What are we asked exactly? Use this observation to suggest strategies for paying the future tuition for a child at a private university, assume no financial aid, and then blah, 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 blah. So I guess we want to quantify how much tuition will be. Or I guess we could come up with a figure every year. Tuition costs will, well, they're asking for strategies. It's a pretty open-ended question. Invest in Bitcoin? I have no idea. Invest in companies that are, invest in asteroid mining? Invest in companies that do neocolonialism to harvest resources from countries that can't fight for their own selves? Really? That's what the question was? Right. Well, let's see. Maybe we can. Well, we can at least define an equation for tuition increase. Have led inflation rates by about. So that's just an observation. Who knows what the future will hold? All right. Well, let's just do some assumptions. Tuition rate will increase. Tuition rate, university tuition rate will continue to lead inflation by 3%. Annual inflation will continue to remain at 5%. Okay, givens. Let's go with that. Math, several equations. What do we got? We got 25,000 is our Ch1. That's it. Okay. C at T1 equals 25,000 USD per year. Use their own method of abbreviation. I is equal to 0.05 plus 0.03 equals 0.08. T1 will equal, call that 2000, I guess. We're going to do that now. Let's just go with 0. T2, let's not define it. Let's just see what this gives us. I guess we should say something about strategy. The question is open-ended. And asks for general strategies for paying tuition costs in the future, given that tuition costs are rising faster than inflation each year. A model A predictive model can be formed, assuming a model of future tuition costs can be formed, given an initial tuition cost. We need some time frame, though. We're not given a time frame. Let's go with let's say 18 years. If you were to say have a child, 18 years to raise the child, and then 18 years is when you'll have to end up paying for tuition. In order to ground the question into more practical terms, it may be useful to assume that an 18-year time period may be useful to assume that no savings for tuition person's tuition has been made, and that the person has yet to be born. It also may be useful to assume that this person may be born in the next year, making this question about how to pay for a future child's tuition, or making this question about how much a future child's tuition will be by the time they are old enough to attend university. Okay, so assumption. 18 years, a child will be accepted, will be born within the next year, and therefore tuition payments will have to be made beginning in 18 years and persisting for 4 years, It's annual tuition payments made beginning 18 years and ending 4 years later. Okay, so we're bringing the idea of integration of this thing. What can we do? So cost is increasing. Do we want to increase or insert the idea of continuous annual rate? Because this is a cost increase per year, not like e to a certain power with a given rate. I mean, they don't ask for that. They just for strategies how to pay for it. Okay. So first, planning to pay for a future child's tuition requires integrating the cost function C of t C over 4 years. This can be done by performing 4 separate calculations where t equals 1, 2, 3, 4. No? T2 equals 18, 19, 20, 21. To play with indices, 2, 1 equals 18. Two, 1, 2, 2, 2, 3, and T4. So the cost total would equal, so C is already rate. So we could do lowercase c, or savings. Yeah, let's do S. Savings equals the cost rate function over 4 years. Adding them together. Something like that. Be nice if I could just do a integration. If I could do something like a integration of the cost function in like an analytical way, that'd be nice. I guess if you made that T2 equal just T, T1, just set that to 0. I guess it could be done. Then you integrate it. You'd have an analytical solution. So this is the not a continuous. This is every year. You have to find some continuous rate. Nah, let's just do piecemeal. It's good enough. It may be useful to convert the cost equation into a continuous one instead of an annual instead of one designed to be evaluated annually. However, to simplify the solution, it is only a 4-year, or say a piecewise summation of costs will be used. Still kind of curious though, what would that look like? Not worth it. Because then you got to turn into an exponential function that matches the same performance, and then yeah, I'm not going to do that. Okay. this is assuming that we have to have... So saving up money for a future child's education. You can save money at a continuous rate. Do we use the other parts and say, yeah, how much they're saving or capable of saving per year? It's just strategies. Do they want me to evaluate multiple strategies to see which one is best? Because I guess what we're doing is finding the total amount that will have to be paid in US dollars at the end of the day. And then we could, once we have that figure, then we can come up with some ideas for how to obtain that money at each time period. Or say at the start of the child's tuition, just have everything paid. Say, have all of the savings S available at the first year of the child's thing, and maybe invest that money in such a way that you can pull out the required amount at the start of each year. I guess you could get fancy with that. But yeah, finding the total cost will probably, each individual cost will be useful to have, I think. Let's do that. So calculate each tuition amount for the child's 4 years university. So do we have an equation? I'll use the same Tref. Use equation, problem 25, CT2, CT1, Tref to calculate. All right. Minus 0 years, 1 years, no, 0 years, no. I guess I have to solve for that first. Let's do that. See. guess we can just do this in one go. 25,000 times 1.08 raised to the 18th power. Hmm. 99,900. That's per year. Because I can remove the full year in my other calculations. $19. Dear. All right. All right, S will be all these numbers. 108, All right, S is equal to $500,000. Wonderful. One strategy for saving up for this amount. For saving up this amount is to have been born to billionaire parents. And have a trust fund. Another strategy is to another strategy is to reduce the amount of inflation, reduce the rate at which tuition costs increase. This may require another strategy. This may require government intervention in how scholarships are provided. Or another strategy is to use competing non-university solutions for educating. Another strategy is not to send children to university for their education. However, the problem seems to insist that require that a child be sent to a private university. Therefore, here are some strategies for acquiring the monetary wealth necessary to participate in such a system. Invest money so that invest because I should do this. Invest money in enterprises that provide a return on investment at or exceeding 8%, or exceeding the rate of increase in tuition prices for the target private university. Let's see here. Due to its nature, due to the exponential nature of a cost rising faster than inflation, a rate higher than, due to the nature of exponential cost increases, the cost of tuition for an ordinary citizen of a rise to unreasonable levels, so that only the super rich may participate, be able to pay for children to attend private universities if private universities all rise if all tuitions rise at the same rate for it. Here are some strategies for acquiring adequate monetary wealth, such as system or reducing the system. Given reasonable investments in reduce the rate at which tuition cost increases per year, so each year, so that it does not exceed the rate of inflation. This may be achieved by changing the choice of private university to one with lower annual tuition cost increases. Invest money in enterprises that provide a return on investment at or exceeding the rate of increase in tuition prices for the target private university. So basically, change universities so they don't cost so much, or invest money so that return on investment is higher than the rate of increase in tuition. That's pretty much it. Buy a lottery ticket. Yeah, no. I mean, that's, in the general sense, really, that's all I can think of. Things that are somewhat reliable and reasonable. Okay, I'm going to call that good. I guess I should say that it's the cost is orders. The cost of 25,000 quickly increases by an order of magnitude after about 21 years. let's see, 126,000 times 1.08. So that's 22 years. 23, 24, 25, 26, 27, 28, 29, 30. So after 30 years, it's shown that the cost of for comparison, this comparison, this is approximately 5 times as much as it would cost to send a child to the same private university at time equals 0. When tuition costs are still nearly around 25,000 USD per year. In other words, every generation, assuming that a citizen abstains from starting a family until they have graduated from university, the cost at a tuition cost increase of 8% per year results in the cost of tuition rising by a factor of 5 every generation. I guess if you just assume that the inflation rate is baseline and everyone's salaries keep up with inflation, then say person today's equivalent of $25,000, 1 year times 1.03, 2 year, 3 year, 4 year, 5 year, 6 year, 7 year, 8 year, 9 year, 10 year. 10 year, it's about a, so 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So about 24, after about 24 years, assuming that cost of living only the 3% beyond tuition, or 3% beyond only the 3% beyond the rate of inflation is relevant, then example, and that 25,000 USD per year is a reasonable amount to pay for tuition at present, then it takes 24 years for tuition to become double what? Double that which is considered reasonable in the present. So let's put that into an equation. That's basically saying how long does it take for 50,000, 25,000 to equal 1.03 raised to time Did I solve for time earlier? I thought I did. I solved for rate. I'm just solving for t right now. Okay, that's about all I can say about that subject. It's kind of an open-ended one. You can kind of go where you want. It seems to be pretty practical and relevant, but that's all I'm going to put on that one. That ended up being a few pages. Okay, so yeah, summary. Let's go back to the prompt. Okay. So we are given pump price of gasoline of at that starting figure. 30 years has passed. We're given a rate of inflation 5% per year. And so if we assume that gasoline price tracks inflation, we find that gasoline price increases to $1.5. Yeah, so it about quadruples every 30 years, according to this model. Part B, engineer starting salary at $16,000 in 1970, rises to a salary of $80,000 in the year 2000. His salary is just barely keeping up with inflation at 5.5% per year. Tuition increase, blah, blah, blah. How to pay for tuition for a child at a private university? Well, asking this question is a little bit too late since the child reading this is already at the private university, so RIP. Parents, assuming no financial aid, an annual inflation rate of 5% per year, and a current tuition rate of $25,000 per year. Okay, so strategy. So we go ahead and calculate for part C what it would cost to send a child to university for 4 years. And then we say, all right, that's well and good, but what about if, like for comparison, this amount in the future might be considered like, oh, that's not too bad. That's like the price of a car or something. So if we assume that $25,000 per year is like on the bare edge of what is considered reasonable, then maybe a useful metric is to double that and say, okay, how long does it take for that tuition cost to double? And so we can put that ratio into the thing and find out, and it comes out it's a doubling tuition costs. This 3% is doubling, so it takes about 24 years for tuition to rise beyond twice that, which is reasonable at a time. I'm assuming that what is considered reasonable is the baseline 25,000 figure that increases itself by 5% per year. So we're just considering the 3% beyond inflation in this figure, assuming that, yeah, everyone's happy with inflation, which I'm sure some libertarians or some other folks would consider that bad. Regardless, all right, then I just go ahead and say, answer the question about asking for strategies and to pay for attending a private university. One strategy is to just reduce the rate. Choose a different private university that's lower cost. The like certifications and other means of learning skills and networking with people seem to be what I think personally are going to be the future. Everyone gathering into little cesspools of pandemic viruses in a single spot seems to not be very useful. Learning from home, I think, might be something that is actually more common in the future, speaking from the year 2020. Yeah, like going to university to pay for having your tuition be used to pay for new stadiums so sport ball people can play sport ball. It just doesn't seem very interesting to me. So yeah, you can choose a different private university or a different method of learning altogether, I think, is what I'm trying to get at with this one, but I can't say as much without going beyond the bounds of this question. And then the second one is, okay, just earn more money. Why don't you just earn more money, to go to university? Okay, well, in general, that idea is, okay, invest money in enterprises that provide a return on investment at or exceeding the rate of increase in tuition prices for the target private university. Very bland answer, but it does get at the core, I think, of what this question was aiming for, which is Earn more money so you can pay more money to McGraw-Hill. Great. Whatever. That's all. That's the summary. That was problem 25. That concludes chapter 1 of Introduction to Introduction to Chemical Engineering Thermodynamics by J.M. Smith, H.C. Van Ness, M.M. Abbott, 7th edition. So this puppy was written and published in the year... When did I get this? This was for my class of 11. So yeah, this was 2005 seems to be the last copyright date for this 7th edition. So yeah, current as of the year 2005. Hooray, chapter 1 done. How many more chapters are there in this book? There are 14, 16 chapters, looks like. Quick list of chapters. Let me do something. Quick list of chapters are next chapter. Chapter 2 is the first law and other basic concepts. That includes state functions, phase rule, enthalpy, heat capacity, and the idea of mass and energy balances for systems. Chapter 3 is volumetric properties of pure fluids. So this is when we get to the virial equations of state, the ideal gas law, then correlations for gases and liquids. So in other words, gases and solids and things have properties, and we can have equations that model those properties. Those equations, there are some analytical idealized things that help model reality, but those equations are often empirical. They're just a lot of people like grad students measuring very carefully how things react when they change conditions on them, temperature, pressure, and such, and recording the resulting effects and trying to come up with equations that fit. So the idea, the strategy, it seems like why these things have value is so that you can plug them into process simulators, things like computers that can do the calculations automatically and save you time for having to do those, which in a sense, the end result is that you have a much firmer and tighter grasp of reality, which is needed in places such as factories or process plants where you're manipulating matter at huge scales, and you want to eke out every bit of efficiency out of these transformations, which is pretty neat. Heat effects. I wonder if the WorldCat thing for this, let's see, might, let me see if I can pull up in TechMax the link for this textbook, because I'm doing this as a personal review of this subject matter in a way that I think other people can benefit from. So let me go here to browser. Yeah, there we go, Chromium. So this is WorldCat. This shows this textbook, and I'm hoping that there is a list of chapters in the thing. Okay, great. Let's see. Let's go ahead and get these things. Yes, I accept. Can I move? Nope. Okay, that's better. So where was I? Yeah. I'm just reading from the table of contents, actually, from this book, but you can follow the things here. So I was talking about first law and other basic concepts. Next is heat effects. So chapter 4 is heat effects. That talks about sensible heat, latent heat, standard heat of reaction, formation, combustion, enthalpy, again, delta H. So this would be things like concepts that are necessary for heat transfer, which comes up later, I think. Chapter 5 is the second law of thermodynamics. Oh, there it is. So that's where we talk about entropy and ideal work. It says here, the third law of thermodynamics, heat engines. So this would be getting into like steam engines, what exactly is going on, cycles, heat source, cold, hot sink, cold sink. basically how to perform work given a source of high temperature and a sink of low temperature, and how you analyze such systems for efficiency. Next is Chapter 6, Thermodynamic Properties of Fluids. So, chapter says it talks about two-phase systems, residual properties, property relations for homogeneous phases, residual properties of equations of state, thermodynamic diagrams. I'm a little fuzzy, actually, on what this is talking about. I'm guessing they're talking about, like, vapor pressure and such things. Let me see, do I have any notes scribbled in this chapter? Mollier diagram. Okay, that sounds familiar. Okay, residual properties from the virial equations of state. Okay, these are more close empirical methods for determining properties of thermodynamic properties like enthalpy, entropy. Yeah, so a bit more of figuring out how the different state functions work together. Like potential, like the total energy of a system, U, entropy of a system, S, enthalpy of a system, S, or H, excuse me. And several equations for how those all mash together. And 7 is applications of thermodynamics to flow processes. That one sounds a little interesting. Duct flow of compressible fluids, turbines, expanders, and compression processes. So these are more praxic, more things that are more grounded, I guess, in hardware. So nozzles, valves, throttling, the idea of supersonic flow. Compression, so taking gas, compressing it, how it heats up, how the pressure rises, entropy effects, which are all important for like gas transfer lines or even rockets that are going into space. How the molecules flung through a rocket nozzle flow. That's all. I don't think this book goes into rockets itself, but it does touch on it. 8 is production of power from heat. So we talk about the steam power plant, internal combustion engines, jet engines, rocket engines. Okay, well, there we go. Maybe a little bit more on things involving compressors. 9 is refrigeration and liquefaction. So moving heat around, heat pumps. When you compress a fluid, it heats up, and when you depressurize a fluid, it cools down, usually. And so that has a bunch of efficiencies involved in that. Vapor-liquid equilibrium, 10. This is some fun stuff. So you put a bunch of water into if you take a bunch of water and you squirt it into a box that is just a vacuum, like nothing inside the box, not even air, the water, a lot of it will start to sublimate immediately, but water vapor will come off of the liquid water and fill that container, that box, with gas. That gas being just water molecules. And there will be a point where the pressure inside that box will increase. There'll be a point where it will no longer increase. It'll just be at a steady state, where the transfer of water molecules from the liquid into the gas equal the rate of condensation of water vapor molecules into liquid phase. Vapor-liquid equilibrium, fun stuff. That's important because, Raoult's law. Just how equilibrium works, since it's a phenomenon that's important in like distillation, and it's important because it's a rate-limiting step. So when you mix two chemicals together, often the reaction rate is bottlenecked by how quickly the molecules can come into contact with one another, which means that the molecules have to diffuse through some medium, be like a solution or like the rubber of a balloon or something, like of a membrane. Like there's Equilibrium is kind of like an upper limit for how fast molecules can mix from one area of stuff to another. So yeah, it's an important concept. Then 11 is solution thermodynamics theory. So again, going into solutions, we got fugacity, being the effective partial pressure is kind of my mental bookmark for my mental note for what fugacity is, but I guess I'll get into that when I get to chapter 11. Ideal gas mixture model, generalized correlations for fugacity coefficient, ideal solution model. So phase equilibria, chemical potential, getting into kind of the more like gnat's ass, like the very close tracking of how liquids work and how gases work and how they flow from one to another and why they flow from one to another, like energetically. Why is such a thing favorable for a group of molecules to condense from vapor phase to liquid phase? Like there's an energy cost associated with that transfer, and you can, like if you don't want something in liquid form, you want to evaporate it, then you can use these equations to figure out exactly how many kilojoules you need to pump into a system to make that kind of vapor. And yeah, things like that. 12, solution thermodynamics applications. That's kind of a little bit more boring, but it seems to be models, heat effects. What is in there, actually? I don't have any clear memories of that, actually. I guess just applications of what I just talked about. Enthalpy diagrams. Oh, yeah. That. When heats of solution, heat of mixing processes. Yeah. If you mix water and ethanol together, you get heat just from the mixing process. Fun. That's kind of the idea of what I was talking about. Excess gives energy. Okay, anyway. 13 will be chemical reaction equilibria. Great. So another, again, equilibrium. Talk about what's in here. At the end, fuel cells, which will be interesting. Application of equilibrium criteria to chemical reactions, effective temperature on equilibrium constants, how they're evaluated, relationship of equilibrium constants to composition. So K values, if I'm not mistaken, this would be all about reaction rates. Like if you have a reactor going, the reaction can take place in liquid or gas, and the rate of reaction, often you want to make that as fast as possible, or maybe there is a problem in terms of excess heat. Like maybe you want to slow a reaction down so it doesn't go too fast because it's already exothermic. So you need to calculate really closely how much heat is produced. And so the rate of a reaction often requires that molecules go through several steps, and these steps are rate. One of those steps might be rate limiting. So a molecule going into an intermediate stage 1 to an intermediate stage 2 into a final state, the transfer to the first intermediate stage might be very fast, but the transfer to the second intermediate stage might be slow. And even though you can it doesn't make sense to try and facilitate the first transfer stage, you want the first transformation, you want to focus on the second transformation because it's the slowest. So things like combustion, like that might be relevant. And yeah, and then 14, topics and phase equilibria. More correlation stuff, looks like. Vapor liquid equilibria, osmotic pressure, liquid equilibrium, vapor liquid equilibrium, solid liquid equilibrium. These seem to be more kind of a review / reference of many different topics which have thermodynamics involved with them, but maybe not necessarily like needing their own chapter. Each one could be their own book, but this is an introduction book. It's not meant to be a comprehensive review of everything in chemical engineering, thermodynamics. Then we got, 15, thermodynamic analysis of processes. Thermodynamic analysis of steady-state flow processes. Where is that? 15? Yeah. I don't recall anything of that, actually. Steady-state flow. Is that just maybe covered more in plant design that I took? 635. What do we got here? Looks like it's more of a analysis of process equipment. Like, it shows a PFD, and then the chapter just reviews, like, takes everything that has been introduced in the book together and asks questions. Yeah, it seems to be more a way to just group a bunch of capstone ideas together to be reviewed. Then 16, Introduction to Molecular Thermodynamics, which seems to be getting closer to like something that might be relevant for nanotech. Atomic precision manufacturing, atomically precise manufacturing. Things where you're worrying about individual molecules, which I don't think we did very much of. And this certainly doesn't talk about such nano machines, but it does talk about the statistical mechanics of stuff. So like at the molecular level, where atomic size, molecule size is actually important, a lot of the macro properties you see, like say the boiling point of carbon dioxide, are functions of things like how are electrons distributed in the cloud surrounding the oxygen and carbon atoms in CO2, like the sloshiness of electrons in that molecule. I think from my understanding, they affect how that molecule is attracted to other molecules moment to moment. Like there's a time element that's relevant. And so when you start to try and figure out how, like if you try to predict those macro properties from these micro features of time, electrons moving around, and charges, temporary local charges in the molecule, then yeah, you need to go into statistical mechanics. And I took that as a completely different class, so I don't think we covered this in this textbook. It'll be fun to just kind of review what we got here. Pauling electronegativity for some nonmetallic metals. Hydrogen bonding and charge transfer complexing. That sounds interesting. Thermodynamic properties and statistical mechanics. That's what I was talking about. Ideal gases. Internal energy. Microscopic view. Yep. Fun stuff. Boltzmann constant looks like is in there. Boltzmann constant times temperature. Quantum this, quantum that. That'll be kind of interesting to get into. And that's, I think, the last chapter. And everything else is just tables and appendices that are useful in doing stuff. So, yeah, we finished Introduction, which it took me several tens of hours to do. But I did do all the problem sets. All 25 of them. Here in a bit, I'll start with Chapter 2 and start going through all those. It'll take me a few days to read through the material, just so I understand it. But I'll go ahead and give a quick review, I think, in a video later on, and then I'll start on making separate videos for each problem. Chapter 2 looks like it consists of 44 questions. So 44 questions, a lot of which are multi-part questions. So it might take a while, and maybe a lot of them are going to be kind of just reviews of one another, but at least I won't have to be bogged down by things like gravity, like pound force, pound mass problems. Doing a quick check, and I don't think I see very many. Yeah, they're all in kilograms and Kelvin and Celsius, bars, cubic centimeters, moles. Yeah, great. I'm glad I got rid of those things. First chapter is probably just, okay, if you are... Chapter 1 is probably to exercise you from imperial units, and at least show you how metric units are done, because the rest of the book seems to be done in those units. We might come back to BTUs and things like that for steam engines, because a lot of that engineering literature is in that language. Okay, great. Thank you for joining me. I will get on this, I think, maybe later today. Or probably not today, probably a few days. Anyway,